Welcome to my video lecture series. Today we are continuing our magnetostatics series of lectures in which we are going to discuss what is called force between two parallel current wires. Okay. Now we have seen in the last chapters, like whenever there is some current in a wire, it produces some magnetic field B at a distance r from it. Okay, and whenever we place a current wire in a magnetic field, it experiences a force, okay, given by F equal to I into L cross B. Based on these two factors, okay, if I take two parallel current wires, okay, what will be the force acting between them? That we are going to discuss now. Okay, now consider two wires like this, current wires, parallel to each other. Okay, one is carrying a current I1, other one is carrying a current I2. Distance between the two wires, let us call it as D. Okay, this is a current carrying wire, this is another current carrying wire. Both are parallel, carrying currents I1 and I2, separated by distance D. What is the force between these two wires? We have to see now. Okay, now in order to consider the force, now I'll change the picture from this view to the perpendicular view like this. Means I'll imagine both the wires are going into the board like this. Okay, when we take that aspect, the picture will be looking like this. Okay, this is one parallel wire carrying a current I1 into the board. This is another wire, okay, carrying current I2 also into the board. Distance between the two wires is D. Now in this picture, the wires are carrying currents into the board like this. Okay, separated by distance D. Now because this, forget about this second wire for some time. This is a current carrying wire which produces magnetic field around it. What is the direction of the magnetic field? Given by our Ampere's right hand rule. Hold the current carrying wire in your right hand with thumb in the direction of the current. Curling right hand four fingers will give you direction of the magnetic field. Curling right hand four fingers will give you direction of the magnetic field. That is, because of this current like this, there will be magnetic field lines, concentric circles like this. The magnetic field lines will be like this. Okay, in this direction, this way. Now at the point of second wire, okay, the magnetic field will be like this. It will be pointing down like this. In this direction, magnetic field will be making a circle. Okay. Now because it is the magnetic field due to the current in the first wire, I'll call that field as B1. Okay, so that B1 at the point of second wire will be pointing vertically downwards like this. And now the situation is, there is some magnetic field B1. What is that magnetic field B1? From Biot-Savart law, we have B1 equal to mu naught I1. Okay, current due to an infinite long straight wire, mu naught I by 2 pi r. Okay, that current is I1 in the first wire, and this wire is at a distance D from it. So B1 equal to mu naught I by 2 pi, instead of r, the distance is D. Okay, this much magnetic field B1 is acting vertically downwards at the place of second wire. Now second wire is a current carrying wire. It is carrying a current I2, and on that current wire we have this magnetic field due to the first wire. Okay, so what is the force experienced by the second current carrying wire because of this field B1? Okay, now that force on the second wire, I'll call it as F2, is equal to, right, I into L cross B. Okay, what is the current in the second wire? It is I2 into its length is L cross, what is the magnetic field acting on it? It is B1. Okay, B1 is the field acting on this wire. Now okay, so F2 equal to okay, L and B. L is like this. Okay, length of the wire is like this, magnetic field is like this, both are perpendicular to each other. L B1 sin theta, sin 90 equal to 1. So it is simply, right, I2 L, it is B1. What is B1? Substitute the value of B1 here. The force on the second wire F2 equal to, right, I2 L, B1 is mu naught I1 by 2 pi D. Okay, that is equal to, right, mu naught I1 I2 L by 2 pi D. Okay, bring that L to the side. Force per unit length of the second wire F2 by L equal to mu naught I1 I2 by 2 pi dl, right? Okay, this is the magnitude of the force per unit length. Now, what is the direction of the force given by Fleming's left hand rule? Okay, forefinger should be in the direction of the field, middle finger should be in the direction of the current, thumb will give you direction of the force. Now, field direction is pointing downwards like this, so I'll put my forefinger like this. Okay, current is pointing into the board, so I have to twist my entire palm into wrist into the board such that current direction is pointing into the board like this, such that the force will be in this direction. That is, okay, the situation is like this. Here, field is downwards, current is pointing into the board, so force will be towards our this direction. So this force on the second wire F2 will be like this. This force on the second wire F2 is in this direction, that is towards the first wire. Okay, what is its magnitude per unit length? Mu naught I1 I2 by 2 pi d. Okay, now come to the second wire. It is also carrying a current. It also produces its own magnetic field around it. Okay, what is the direction of the magnetic field? Again, right hand rule. Current, thumb in the direction of the current. Field due to, right, this wire will be like this. Field lines will be like this. That is, field due to the second wire will be like this, concentric circles, and at the site of the second wire, okay, the magnetic field lines will be upwards like this. This is the field on the first wire due to the second wire. I will call that as B2. B2 direction will be vertically upwards. B2 will be vertically upwards. Okay. Now what is that B2? That B2 is at a point, at a distance D from a wire carrying current I2. So B2 is equal to, okay, mu naught I2 by 2 pi d. Okay, this B2 is now acting on the first wire which is also carrying a current I1. Okay, that is same, I equal to I into L cross B will come into picture, because that is a force acting on the first wire. I'll call it as F1. Okay, right, F1, force on the first wire is equal to, right, what is the current in it? I1 into its length is L cross the field acting on it is B2. Okay, I1 into L cross B2. That is, again, L and B2, L is like this, B2 is like this, both are perpendicular, so L, B2, L, it is simply L, B2. So, I1, L, B2. Okay, B2 is nothing but mu naught I2 by 2 pi d, substitute that value here, and bring that L to this side. Force on the first wire per unit length is equal to, okay, right, mu naught I1, I2 by 2 pi d. That is, now, F2 by L is also mu naught I1 I2 by 2 pi d. F1 by L is also mu naught I1 by 2 pi d. That is, the forces are equal in magnitude. Okay, force F2 per unit length, we have seen it is towards our left. Now what is the direction of this force? F1. Okay, now force is again forefinger in the direction of the field. So put your forefinger in the direction of the field which is upwards. Okay, current is pointing into the board. Twist your entire wrist, okay, such that middle finger is pointing into the board. Okay, thumb will give you direction of the force here. That is, the force on the first wire due to, right, the magnetic field in the second wire is F1 is like this. Okay, right, F2 is acting this way, F1 is acting like this, right? Now what does it mean? These two wires are getting attracted towards each other. That is, whenever, okay, there are what you call two parallel currents carrying currents in the same direction. Okay, the force on this wire due to this wire will be like this. Force on this wire due to this wire will be like this. That is, both the wires will be attractive. Okay, the force is attractive, means the wires get attracted. Okay, right? What is that force per unit length? Force of attraction per unit length means, okay, it will be like this. Okay, force per unit length between these two parallel wires. Okay, the forces will be, F1 will be like this, F2 will be like this. Okay, so the wires will get attracted towards each other. What is that force per unit length? Okay, mu naught I1 I2 by 2 pi d. Mu naught I1 I2 by 2 pi d. Okay, when currents are in the same direction, the force is attractive in nature, the wires get attracted. Okay, when the currents are in opposite directions, what will happen? Okay, when you reverse the direction of the current, right, this F2 will be this way, acting this way, right, and this F1 will be acting in like this. Okay, whenever you change the direction of either this current or this current, Okay, what will happen immediately? Force also will, direction gets reversed. Means F1 will be like this, F2 will be like this. That is, when the currents are in opposite directions in the parallel wires, okay, the forces will be acting like this. That is, wires will get repelled away from each other. Means when the currents are parallel in the same direction, wires get attracted. When the currents are anti-parallel, the force is repulsive in nature, the wires get repelled. Okay, forces will be in opposite directions like this, okay, away from the wires. Okay, they get repelled, we say. So two parallel current carrying wires will get attracted, to anti-parallel current carrying wires will get repelled. That's what we should keep in mind. What is that force per unit length? F by L equal to mu naught I1 I2 by 2 pi d. D is the distance between the two wires. Okay, this concept becomes very useful. It has many applications actually. Questions also will keep on coming. There is a spring like this. Okay, a spring is like this. I'll send some current I through the wire. Okay, what happens? In every turn, current will be flowing like this. Okay, that is, between two successive turns, if you see, currents everywhere will be in the same direction. Okay, whenever two parallel current carrying wires have currents in the same direction, what will happen? Force between them will be attractive, means the wires get attracted towards each other. Means what will happen to the spring? Right, the spring will get compressed like this. Okay, the spring will get compressed. Okay, right, this has an important applications in many ammeters, voltmeters, etc. See, whenever I'm sending 2 amperes of current, what is an ammeter supposed to do? The needle should be should show me 2 amperes or 3 amperes or like that. Okay, there will be some springs inside. Okay, made of phosphor bronze. Okay, special materials. Okay, where the temperature effect on resistance will be extremely small. Okay, depending on the contraction of the spring or extension of the spring. Okay, right, the needle will be rotating like this. Okay, the concept used is the current between two parallel wires. It has many applications. Okay, as we see some problems, the things will become clearer. Things will become clearer. Okay, right, now suppose say the two currents are equal, as in the case same current is passing through every turn. Okay, if I1 equal to I2 equal to I, what is the force per unit length? F by L equal to mu naught I square by 2 pi d. I will write mu naught I square by 2 pi d. Okay, here we can take some numerical values. Let I equal to 1 ampere. Both the wires are carrying 1 ampere current in the same direction or in opposite directions, whatever it is. Okay, both wires are carrying same current of 1 ampere. Distance between the two wires is say 1 meter. Okay, I square is equal to 1, D is also equal to 1. So force per unit length of the wire, F by L equal to mu naught by 2 pi. Mu naught value is 4 pi into 10 to the power minus 7 we know. Okay, by 2 pi means it will be 2 into 10 to the power minus 7 Newton per meter. 2 into 10 to the power minus 7 Newton per meter. Okay, so this was this definition. This is used to define 1 ampere in those days, in the earlier days. Okay, they'll take two parallel wires. Okay, send same amount of current through both the wires in the same direction, such that force will be attractive in nature. Okay, right, and they keep on adjusting the current. Okay, when the force per unit length on each wire is exactly equal to 2 into 10 to the power minus 7. Okay, Newton per meter. The current passing through those two wires is exactly equal to 1 ampere. Okay, that was one of the earliest definitions of ampere. What is 1 ampere? How do you define 1 ampere? Means take two parallel wires, okay, separated by a distance of 1 meter. Okay, right, send equal amounts of current through both the wires and keep on adjusting the current. Okay, when the force between the two wires is equal to 2 into 10 to the power minus 7 Newton per meter, then current in both the wires is equal to 1 ampere. Okay, that was the earliest definitions of 1 ampere. Okay, so based on all the concepts what we have seen, we will solve some problems. Okay, right? Few problems in every lecture, okay, which have appeared in the all important all India examination like IIT JEE or IIT JAM or CSR, okay, JRF. What all problems have come based on this? Of course, most of the problems there will be induction aspect also, electromagnetic induction aspect included, right? And some require some ampere circuit law also. So let us complete ampere circuit law and then go into solving some problems, right? Thank you for this.